This is screencast 4, week 3 for Business Administration 571. I was working on this X bar chart, and I got to the lower control limit formula, X double bar minus A3 times S bar, which equals 4.66 minus 2.659 times 3.301, and that comes out to be negative 4.1107. And so that's the value of LCL right here. X double bar is going to go pretty much through the center of the points, because after all it's the average of all the points. And we see that that's 4.66. We've got a lower control limit of negative 4.1107, so we've got 0 in here somewhere. Now we've got thickness. Of course, thickness can't take on a negative value, so what we have to say is the lower control limit's going to be replaced with 0, because obviously we'll never find a thickness which has a value that's less than 0, so the lower control limit might as well be 0. So if we make a part that has 0 thickness, we should be indicating signal, which is pretty silly, and it begs the question, what's going on here? Well, what's going on is this. You've got X double bar being your best guess for mu. After all, it's the average of the averages. You've got an upper control limit and a lower control limit. And you are observing X bar. If you put a normal distribution on its side, then you have a bell curve which has as area under this curve, or to below the to the left of this curve in this representation, areas correspond to probability. So there's a little chunk of area up here above the upper control limit, and there's a little chunk of area down here below the lower control limit. The probability that the lower control limit is always smaller than X bar observed, and X bar is always smaller than the upper control limit. That probability, if you look at this picture, is this area that I'm shading right now. So this shaded area equals this probability, and it turns out that if we use this formula, where the control limits, well, I think we can just refer back to where I first wrote them down, which is right here. If you use this formula for the control limits, then this probability is 1 minus 0.0027, which is 0.9973. You're thinking, well, so what? I mean, who cares? Well, this is kind of important. Shewhart invented this. Shewhart said the false positive rate or the FPR should be set very low and recommended .0027, which is 1 minus 0.9973. Why did he do that? Well, Shewhart said, look, here's what we're trying to do, saith Shewhart. And after all, he invented this thing and popularized it. He says, we've got ourselves these control limits. And we cry foul when we get a point up here or a point down here. Signal, in either case. What we're really about is this. Here's the original mu, and then here's mu prime, and this is a mean shift. So-called mean shift. We're all about trying to figure out whether or not the mean, this is the mean thickness in our example, or the average thickness coming out of the molding machine. As managers, what we're about is trying to have a good guess as to, and when if, the mean of this molding process that molds a plastic part, and we're measuring its thickness. When that mean thickness changes. If the mean thickness changes, something has happened to the line. The machine or the materials coming in or the way the machine is operated, something has caused the mean thickness to change. And that change is referred to as a mean shift. So the shift has, the mean has shifted from this value to this value, from the value mu to the value mu prime. We want to know that, and we want to drop the line and figure out what happened, because that's a no-no. We do not want to have the mean change during a production run. Now we run the risk of building parts that are out of specification according to our engineering department. That is not acceptable. So how come I have written x double bar equals mu hat, and then I've put mu down here, not right at mu hat, to drive home the point that mu is forever unknown, and the best we can do is estimate it with data. And guess what? Our little estimate, based on 36 observations, got it wrong. Well, we shouldn't use that number. We should use the right number. You'll never know what the right number is. The best you can run with is x double bar. But in reality, the mean is some number, hopefully pretty close to what our guess is, but there's no reason to believe it's going to be dead on. So we're going along, and everything's hunky-dory until we get a point outside the limits. This is the chart's way of saying the mean just shifted at some point a little bit previous to when we got our signal. So Shewhart said, these points, either above or below, could have happened. So you could get a signal with no mean shift. Why? Well, because we're assuming a normal distribution for x bar, and values in the tails, either extreme values this way or extreme values this way, are entirely possible. They're not likely, but they're not impossible. So if our chart squeals and nothing has gone wrong, there's a very old phrase for that. I'll say in this case, the chart is crying wolf. So, you know, you have your sheep in a herd, and you got your shepherd, and your shepherd thinks, oh, I think there's a wolf, so I better go tell all my buddies to come over here and drive the wolf away or shoot it or something. So he starts crying, wolf, 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 and everybody shows up, and they look all over the place, no wolf. Well, what'd you do? What's going on? Oh, it was a badger making some noise in the bushes. Oh, so they all go back to the town, back to whatever they were doing. Next night, oh, there's a wolf, there's a wolf. They go out, there's no wolf. So they're saying, you know, what are you crying wolf for all the time? Because there's no wolf out here. What's the deal? You don't want this to happen if you are running an extremely expensive production system and your chart starts giving you signal and you investigate and you find nothing wrong. In other words, the mean has not shifted. Shewhart says, if you do that a couple of times, senior management's going to get sick of this whole idea, and they're going to say, let's lose the control chart. This is otherwise called a false positive, and the rate is the probability that you will cry wolf. So the probability of crying wolf on the next point is equal to 0.0027. How do I know that? Because that's 0.001365 plus 0.001365. Where'd you get this funny number, 0.001365? Here's everybody's beloved normal distribution. Here's mu. Here's mu plus 3 sigma. And here's mu minus 3 sigma. And this area right here is 0.001365. And so is this area over here. Now back a few, I wrote this formula right here. This is our best guess for the mu plus or minus 3 times sigma hat x bar. Fast forward to this picture, and let's say this is the PDF of x bar I. If so, then mu hat is x double bar, and sigma becomes x bar hat, x bar hat. So we are assuming that the PDF, probability density function, of our subgroup means is normally distributed, and we have arbitrarily, apparently, decided to set the false positive rate to 0.0027, thereby saying that our control limits, this is equal to the upper control limit, and this is equal to the lower control limit, thereby setting our control limits to plus and minus 3 sigmas of x bar. not of x bar. So why do we do this? Why do we use this normal? If n is large, the central limit theorem says x bar I is approximately distributed as normal with mean mu and variance sigma squared over n. So this theorem, which you will find in a 210 book, and I have suggested some in my my Learn ProbStat tutorial. I'll say it again. Find an accessible 210 book and look up statistics concepts used in course. E.g. The central limit theorem. Now the book that is used for 210 here at the Lubar, which isn't the one, you don't have to use that one, but that one I know for sure has a good discussion in it of the central limit theorem. So again, the central limit theorem is really important for this course, and as you can see from this little doodling here, the central limit theorem is driving Schuhart's invention of his X bar chart. And it is how we compute control limits. Now this is an assumption that we're making, and guess what is not so great about this? The central limit theorem says all bets are off if n isn't big. In my example, I'm using n as 2. If you're making a low volume unit, and it takes you an hour to make 1 unit on your line, and you set n to 8, you'll get 1 X bar per day if you're running only 1 8-hour shift. So you'll only get 1 observation of quality every shift. Well, you might have shipped out in the shipping department 8 units that are all from a production line that's out of control, and you won't know that until the next day. So you're under a lot of pressure to use n to the smallest number you can get. And in this case, the smallest number you can tolerate is 2. Why? Because when you compute s squared, what do? You do 1 over n minus 1, sum I equals 1 to n of xi minus x bar quantity squared. Well, if n is 1, you're out of luck because this will evaluate to 0. And it's a no-no to have 0 in the denominator of a fraction. So the smallest you can get is n2. So we can say that n has got to be bigger than 2. But the central limit theorem says I want a large value of n. So business practice encourages n small. But the central limit theorem works better if n is large. So there's a tension right there between how we want to operate how we would prefer to operate, and what the assumptions are encouraging us to do. So in running a manufacturing operation, if there's a problem, you want to know about it soon so that you can take corrective action before too many units get shipped that you'll eventually have to recall, or that unrecalled are exposing you to lawsuits and unhappy customers, neither of which you have any interest in dealing with. Okay, so a few comments are in order about where we've come before I run a SAS example of how you can use software to get these control charts. So comments. One, and these are, some of these are in Ryan. A new quality program will encourage workers to reduce their variance. What is not measured is not managed, is one of the current new business buzz phrases. Nice example of this is what happens to professional football players who have just been hired and are new to a team. We see on TV, as they follow teams, that one of the assistant coaches shows up at the apartment of a new player who's been at camp for maybe a month, 2 months, wakes him up early in the morning and says, "I've got some bad news, we're having to cut you from the team. We collect your final paycheck at this office and pack up and you're gone." How come? Well, your numbers are not where they needed to be by now. What numbers? Well, we're keeping numbers on how fast you accelerate if you're a linebacker, how fast you are once you get to speed, how quick you can turn, and we have been keeping this on our computer, and we know at what point you should be reaching certain minimum values, and you haven't gotten to those values, and we're going to have to cut you. This is standard practice in professional football. So what are these people doing? They're doing exactly what I'm teaching here, except for the control limits. They have metrics. These metrics have to do with performance of the player, and they aren't just collecting just one metric, they're collecting several. They're keeping it all on the computer, and they're firing people who are not meeting their minimums. They are implementing this classic tome for about business. If you aren't measuring something, you can't manage it. That's why they are taking these numbers, because they're managing their players. So you walk into a company and you say, okay, we're going to do a control chart now on this line. What's going to happen is, if you plot sigma squared over time, and this is start of program, you'll see this. And this going down is fear. Literally. Now the workers know that they're being watched, and and their performance is being measured. They start becoming more consistent. What is that going to do to this formula? It's going to take the control limits and shrink them, because this number is getting smaller. So if you institute the control chart here, then what you're going to need to do is recalibrate, maybe more than once, in order to deal with the fact that the workers now are afraid and they're starting to work more consistently. So you'll have to recalibrate your control chart a couple of times until the variance levels out at the best that they can do. End of this screen lecture.